Swayam Prabha. Digital India. Educated India.
Welcome to the Advanced Digital Image Processing and Computer Vision. Today, we will start a new topic for our discussion, that is on camera geometry. In the last lecture, we discussed about two-dimensional projective geometry and also the properties of projective transformation or homography. Now, let us consider the image formation in an optical camera and relate this process of image formation with that projective geometry. As we have already discussed earlier also, that in an optical camera, when the image is formed, the rule of projection of a three-dimensional coordinate point is that you draw a straight line passing through a point which is called center of projection. In this case, it is the center of the lens for the optical camera, and that extended straight line or that straight line itself, when it intersects a plane of projection, that means the plane where these points are to be projected. So, that intersecting point is the projected point of the three-dimensional point P. So, we call this point also image point, and also we call this plane also image plane. Now, we will see that actually this configuration is very similar to what we discussed when we defined a 2D projective space. Only in our definitions, what we assumed that in this case, the plane of projection is between the object and also center of projection. That was just for our convenience. So, here also what we can do for convenience, we may consider that this plane of projection is moved forward at the same distance, say the distance. So, the distance between this plane and this plane, it remains the same. Say this is the distance f and this is also distance f in the forward directions. That means in between the object and the center. Now, we can see that the image looks at the direction, the same direction of the object. The earlier it was an inverted image, now it is a non-inverted image, and the point of projection also accordingly mapped to a point which establishes a one-to-one point correspondences, which means it is an equivalent representation of image plane. Instead of indicating the point in this coordinate system, we will be considering this coordinate system. Now, you may recognize that this itself can be considered as a 2D projective space, because this center, it acts like a origin of an implied 3D space of a 2D projective space, and this plane is the plane of projection or the plane where you define a point of a projected point. So, you can represent a point in this space here itself as you have considered a 2D projective space. So, the distance is f, we can represent, say the point here is say fx, fy, f, or if I consider in a canonical configuration f is equal to 1, then this is equivalent to a point x, y, 1. So, the properties of 2D projective geometry can be extended or can be applied for even for the points of the image plane. So, each point corresponds to an element which is a projection ray in that space, all converging to the center of projection. So, let us now consider the relationship between the coordinates in the 3D coordinates to the 2D coordinate of the image plane. And also let us understand the configuration of this kind of simple imaging system, which we call pinhole camera system, because here the pinhole is the center of lens. It is acting like a hole through which the projection rays are passing, and those rays are intersecting the plane of projections, forming the images. And as I discussed earlier, that instead of considering the plane of projections as it happens physically behind the center of lens, behind the lens, we move this plane of projections for expressing the mathematical relationships for our convenience in front of the lens, so that it lies between the object point and the center of projection, and which gives you the same kind of structure of a 2D projective space that we discussed earlier also. So, just to understand or to note different components or different nomenclatures of this configuration, we say this center of projections is the camera center here, because it's the center of the lens of the camera, and that is what is known as camera center. Then this plane I mentioned already, that this is the image plane, and the three-dimensional coordinate space is called world coordinate space, and so the coordinate system of the three-dimensional points are known as world coordinate points. Similarly, the two-dimensional coordinates of the image point, they are called image coordinates, and it has its own convention. If you notice that in the world coordinate system, this center is acting as the origin, camera center, and there are three principal axes which is defined and which is quite related with the axis definition of the image plane in this configuration. We call it canonical configuration. So, some of this definition is that the first thing is the image plane is placed at a length, focal length f, and the principal plane is the plane parallel to image plane. That is, principal plane is formed by xy plane, and the principal axis is the optical axis. So, the coordinate convention of the 2D image plane, which is related to the overall 3D coordinate system in this fashion, that the origin of this space is origin of these coordinates, image coordinate in this configuration is the intersection of the optical axis or principal axis with the image plane. That is how it is defined as the point as the origin. Actually, this point has a name, it is called also principal point. And then the axis what is defined in the image plane, those axes x and y axis, they are also parallel to the principal axis x and principal axis y of the three-dimensional coordinate system. So, this is how these coordinates are related, how the image plane is placed with reference to the three-dimensional coordinate convention. Now, when we want to relate these particular coordinate values, say the image coordinates with the three-dimensional coordinates, so let us consider the corresponding point P, and this is the ray which is shown by the green line. Now, if I take the perpendicular drop of this ray from this point to the xz plane, if you can see that the xz plane, then the point is denoted as x0z. We form a triangle, and where these two are parallel lines, and the length is, this is f, and this is intersecting at z. This is intersecting at z. So, if I use the law of similarity of triangles, so what we can do, that ratio of this length of these two sides, that should be equal to ratio of length of this f is actually defined here. This is the here. So, the ratio of this length. So, this is z. So, ratio of length of this triangle and the other triangle f by z. So, this is one equation, and from there we can get the relation that x equal to f into capital X by z, where these two are world coordinates and this is image coordinate. In the same way, if I take the perpendicular drop on the yz plane and say this is the point in the yz plane, and then we form the triangle with that particular projected line, projection of the 3D line, then this becomes, this is the length of the y coordinate of that point, and this is the length of the y coordinate of this image point. So, again with this triangle, which is shown by this this violet line. So, there is a smaller triangle. Once again, the side here it is f, and the other side here it is z. So, here also we can write in the same way y by capital Y, which is the image coordinate of that point, y coordinate of the image point, and this is the y coordinate of the world coordinate point or 3-dimensional scene point. That is again equal to f by z, and from this relation you also obtained this one. So, you get these two equations, and these two equations can express the relationship between the world coordinates to the image coordinate. Now, we can see that this relation can be expressed in a simpler form, in a linear form, when we consider this is as a mapping of a 3-dimensional projective space to a 2-dimensional projective space. I have already discussed that in the 2-dimensional projective space, you have the image point, and there is an implicit 3-dimensional system where the origin forms the center of projection, and each ray passing through this point, they make the element of the projective space, and this particular point represents that ray. And when we are considering a projection plane, image plane at a constant distance along the z axis, say at a distance 1. So, we can consider, say, this point we will write in the implied imaging system as xy1, but this is equivalent to any point as kx, ky, k lying on that same ray. So, this in a projective space, whether it is xy1 or kx, ky, k, they are equivalent, and we call the representation of image point into this form as the representation in the homogeneous coordinate system. So, we have used a column vector to represent this point, and the third dimension is the scale dimension. So, for an observed image point, the scale dimension would be always 1, because if you divide the scale value with these coordinates, then you get the actual coordinates in the real space. Now, this is about a point, image point in the projective space. What about a point in the 3-dimensional space, like we have discussed earlier, say a point with coordinate x, y, z. Now, this point in the 3-dimensional, now as you can understand that they are related with the scales. So, they will be proportional to xy1 with this interpretation of the projective space. But let us leave aside that interpretation, let us consider themselves, this point itself, a point in a 3-dimensional projective space, which means that the whole 3-dimensional volume, say let us consider a volume of 3-dimensional space, the whole 3-dimensional volume itself, say this is x, this is y, and this is z. So, this value we consider, let us consider that becomes an hyperplane to a hypothetical 4-dimensional space where there is a center of projection for the 4-dimensional implied space or 3-dimensional projective space at the origin of that 4-dimensional space, and all the points are connected through all the points are lying on the line connecting to that point and the origin, which means that in the same format of 2D projective space, we can represent a 3-dimensional coordinate point also in a homogeneous coordinate space, which becomes an element of the 3D projective space then in this form, where the additional dimension represents a scale, and the scale value has to be 1 for the real 3D coordinate point, because those are the observed point, and if I divide the coordinates with this scale, I will get back the real coordinate value. So, this one is again equivalent to, in the same way, by all the coordinates multiplied by a scale k. So, this representation is also called homogeneous coordinate representation. Now, when we talk about this relationship, that means the relationship between the coordinates, image coordinates, and the 3D point coordinates, 3D coordinates of the scene point, then can we express this relationship in a linear form? Now, we can see that there is if we use this homogeneous coordinate system, this can become a linear operation, because here itself directly when we are using the real coordinates, real space, these two are not linear expression. As you can see that the function of when x can be written as the function of x, y, z, and say y could be written as the function of x, y, z, these two functions, they are not linear. That we can easily verify. But when we are considering the input is we are projecting, we are mapping a point in the 3D projective space such this to a point in the 2D projective space, then we will see that those functions become linear. So, let me write this expression here, show this expression here. So, you can see that this is the expression, and it is simply a matrix multiplication. This is a 3x4 matrix which is multiplied with the respective 3D point expressed in homogeneous coordinate system, and which becomes an element of the 3D projective space. And then if we multiply, then what you get first row with multiplication will give you fx, f multiplied by x, second row with this will give you fy, and the third row will give you z. So, you get also a point in a 2D projective space now, because now you get this dimension as this value as a scale dimension. So, if I consider the conversion to the real space, real observed point, to make the scale 1, x becomes equal to fx by z, fx by z, and y becomes fy by z. So, this matrix, this representation, since it is a linear operation, so this makes your projection is also a linear operation in the imaging in your imaging system. Now, there is since this is a projection from a 3-dimensional projective space to a 2-dimensional projective space, we call this projection matrix is the canonical matrix, we call this matrix as a projection matrix. So, you see that it is a transformation, but it is a projection matrix, it is not projective transformation. So, projective transformation is a linear transformation from a 2D projective point to another 2D projective point, or 2D projective space to another 2D projective space. That is what is projective transformation. But when you are calling something as a projection matrix, and the transformation using that projection matrix, you are transforming, you are mapping a 3D element of a 3D projective space, or you are mapping a 3D projective space to a two-dimensional projective space. Further, we have also seen that this expression came from a particular configuration, and we call this configuration is canonical. Of course, in canonical form, we also consider f is equal to 1. That is purely canonical. Otherwise, it's a bit semi-canonical form where we are only using the f as a parameter of the imaging system, which is the focal length. Otherwise, we can assume that the focal length equal to 1, and then further, we can go on generalizing the imaging coordinate convention that I will be discussing in subsequent. So, as I mentioned, this is the projection matrix. Now, we can represent this projection matrix as a factors of two matrices. We can factorize this projection matrix into two parts, into two components. You see, this part is a 3 cross 3 matrix, and this part is a 3 cross 4 matrix of the same structure of the projection matrix. And the interesting part is that the 3 cross 3 submatrix of this 3 cross 4 matrix is an identity matrix, which I am showing also in this representation. And this 3 cross 1 0 column vector is represented as simple 0 here, which means it's a 0 column vector. So, this representation is a representation of a larger matrix using its submatrices. And for the submatrix components, you should know the dimension. So, which though I did not mention, but it is always implied in this form. This I is an identity matrix and of 3 cross 3 size, and this 0 is a 0 column vector of 3 cross 1. So, with this arrangement together, you get this 3 cross 4 matrix. Now, this separator is shown just for convenience. Otherwise, no, it does not have any other mathematical significance. Just it is a separation of this column from this column vector from this submatrices. The other factor, which has been shown as a 3 cross 3 matrix, is also can be represented in a short notation with this convention, since you note that this is a diagonal matrix, and the elements of diagonal that can be listed to denote a diagonal matrix. Now, if we consider this point, now you can see that if I make f equal to 1, then this projection matrix itself, this matrix. So, this is a true canonical projection matrix. And then rest the coordinates. So, after you get the mapped point, after applying this projection matrix, canonical projection matrix, that means I will consider the 3D world coordinate point in the homogeneous system. Then I will apply the canonical configurations, projection mapping, that means projection matrix. So, this is the canonical form with my representation. Then I will get here a projective, an element in the 2D projective space. So, that is the image coordinate in the canonical configuration. Further, this coordinate is again transformed by a 3 cross 3 matrix, and which you can also consider as if a transformation of a 2D projective space to another 2D projective space, because you are getting the respective point, say fx, fy, f in the as an element of the of another 2D project. So, it is a transformation from one 2D projective space, this is the canonical image space, to the transformed image space or observed image space in the homogeneous coordinate representation. So, this diagonal diagonal matrix itself is forming this transformation, and this is acting like a homography, because it's a mapping between a 2D projective space to another projective space. So, this is when we are using a in the canonical configuration, instead of focal length equal to 1, that means the image plane at a distance of unity, when you are using a focal length of f, which means image plane at a distance of focal f, then we need only this kind of transformation to get the mapped points. So, let us further see that how in a more general configurations these coordinates could be related. So, first we will be consider a configuration where you have the offset of principal point. So, I already mentioned a principal point is the point of intersection of the optical axis, which is the z axis in the canonical form, with the image plane, which is placed at a distance f in this case particularly. Now, and then in that system we have always assumed that this principal point is also the origin of the space. But let us assume that origin of the space is shifted somewhere. Say this is the origin. So, in my coordinate convention, principal point does not have 0, 0 coordinate, which means it lies on a coordinate, say px and py. Say this is the coordinate convention. Say this is your origin in your coordinate space, and this is your principal plane. So, once you have computed, say once you have observed xy in the canonical setup with respect to this coordinate transformation, what happens that this becomes the new transformation. This will be observed as, say, we can express it as basically this translation. So, it would be x plus px, and this one would be the y would be y plus py. So, we can write that y prime is y plus py and x prime is x plus px, which means that if I express in terms of your coordinate transformation, the relationships can be written x prime equal to fx by z plus px and y prime equal to fy by z plus py. Now, this once again can be represented in the form of linear transformations using the homogeneous coordinate system as before. So, this is so we can see that this is the transformation. You get the respective three-dimensional projective point, or in the homogeneous coordinate system 3-dimensional points x, y, z 1, and then you are multiplying with the projection matrix which has these new 2 parameters here. Now, you observe that if I multiply how my these coordinates looks, what is the transformation? Say this should be equal to, in the x coordinate, the first row and the column. So, if I multiply them, it would be equal to, say, fx plus px into z. Similarly, for the second row and this one, it will be fy plus py into z, and this will be simply z. So, which means that this scale value, if I divide, this will give me fx by z plus px. So, this is what is x prime. This is would be the observed x prime in the respective homogeneous coordinate system when the scale is 1, and similarly y prime would be equal to, so this divided by z. So, it is fy by z plus py. So, that is why this represents this coordinate, this transformation matrix itself represents takes care of the offset of the coordinate image coordinate system or offset of the principal point, coordinate of the principal point at px py. So, px py becomes another parameter, because in your camera coordinate convention, image coordinate convention, it is not necessary that your origin of the image coordinates would lie at the principal plane, the principal point. It may lie at some point. Usually, it lies in the pixel coordinates. As you know, it lies at the, in our convention, the 0th row and 0th column would be the topmost and leftmost point. So that's why this kind of transformation is required. With respect to that, we have to define this offset. Once again, we observe this is the canonical projection matrix in the form of I and 0. So I means the identity matrix and 0 is this column vector. So this is the canonical form. We can separate it out. And this 3 cross 3 matrix, now we have another 2 elements, Px, Py. So these 2 elements are there, and this matrix also is denoted by this notation K. We will see that uniformly this notation is used. And there is a separate name of this matrix, which is called camera calibration matrix. So K is called camera calibration matrix. And you can see that the structure is once again 3 cross 3, which means it's an homography, and it is transforming the canonical image coordinates to the observed image coordinates in the real space. So this is what it is doing when it takes the text considerations of the takes the generality of representations of the origin at any place. And the total relationships, just to note once again in our convention. So now I will be using these bold fonts to denote the column vectors. So the capital one would be used for representing the scene point in the homogeneous coordinate space, and the smaller one with the bold font will represent the respective image point in the homogeneous coordinate system. So this is how we will be using. So that was the shifting of origin in the image space itself. Now, what about the shifting of world coordinate itself? So far we have used the camera centric coordinate system in our canonical configurations, as we discussed earlier. As you can see here, the origin is implied at the camera center itself, and the axes all are defined with respect to the imaging configurations of coordinate axis of image plane. But it may be in a more general case, world coordinate has a separate convention. So you have defined without the dependency of your camera coordinate system or imaging configurations, a fixed world coordinate system